Hello everybody, welcome to week 2 of the data analytics subject. Today we'll be looking at data. So first off we'll be looking at something called CRISP-DM, which is a data mining methodology. Then we'll be talking about some very basic concepts associated with data, so instances, which are the rows of data that we're looking at, and attributes, which are the things that we know about each data point. Then we'll be looking very briefly at a tool that we might be using this semester. So we'll be looking at something called R, which is a statistical language, and Rattle. We'll also be looking at another tool called KNIME, which we might also be using. Then we'll be looking at the different kinds of attributes, the different kinds of things that we can know about data. We'll go through a couple of different kinds of data sets, and then we'll look at some data understanding. So first off, let's look at CRISP-DM. So CRISP-DM stands for the Cross-Industry Standard Process for Data Mining, and it was a methodology that was developed in 1996. You can see from this diagram that it rotates around data, and there's 6 different phases that are associated with it. Business understanding, where we're trying to understand what the business question is. Data understanding, where we understand a bit more about the data that's being used. Data preparation, where we modify the data so that we can use it for data mining. Modeling, where we do the actual data mining. So you'll remember from last week that there were 2 types of data mining. 1, making sense of the data, and 2, making predictive models. So that modeling is all about those 2. From then we go to evaluation, where we evaluate the quality of what we're doing. We might go back to data understanding if we haven't solved the problem, or possibly we go to deployment, where we deploy the model in the company. So CRISP-DM, it's a standard methodology that's used for doing data mining. There's actually there's lots of different methodologies that are used for data mining. The 2 main ones are CRISP-DM, and the other one is called SEMA. SEMA is put forward by the SAS Corporation, and they develop software that's used for doing data mining. But CRISP-DM is interesting because it's industry neutral, tool neutral, and application neutral. So it's not for a specific industry, it's not for a specific tool or piece of software, and it doesn't care about the type of application for data mining. So CRISP-DM was developed in 1996 by industry leaders from all over the place, and input from more than 200 users, tool providers, so people like SAS and other people, and service providers, among other people. And as we said before, it breaks the life cycle of data mining project into 6 phases. Just like other methodologies, it's trying to be a methodology that suits a whole lot of areas, or a whole lot of different kinds of projects. So big projects and small projects. So like any other methodology, you need to tailor it to the problem that you're using. So not all the steps of the phases might be required for all projects. It might be enough to simplify it and to simplify the steps. The CRISP-DM methodology is described in a really nice journal article, and that's listed there, so by C. Shearer in the Journal of Data Warehousing. So let's look a little bit at the different phases. So the first phase is business understanding. Here we're trying to understand the project objectives from how the business sees it. So we're taking a business view of the problem we're trying to solve. And we're going to go through these in more detail in a moment. Next stage is data understanding. Here we're collecting the data from around the company. We're assessing the quality of the data. We might be doing some early data exploration to see if we can solve the problem straight away. Third phase is data preparation. Here we're constructing some data. We might need to construct data from other data. We might be transforming the data, and we might be doing cleaning data. Well, not we might be cleaning data, we'll almost certainly be cleaning data. And that data is going to be fed into the modelling tools. Fourth phase is modelling. Here we're trying to select and apply different modelling techniques and then find the best parameter settings to get the results that we want from the models. In the fifth phase evaluation, we're evaluating the model in the context of the business problem that we were originally setting out. And six, we're deploying the knowledge that we've gained back into the business. And this is a picture of the 6 phases again. So let's first look at business understanding in a bit more detail. So the kinds of things we're interested in doing here are determining the business objectives, and here, we're trying to understand the business question. So what do I mean by this? The business question is the problem that the business wants to solve. So forgetting about all of the data mining, what question is the business trying to answer with this data mining project? So for example, the business question might be, which customers should I target with this advertising campaign? So note, we're not talking about any of the data mining. We're not talking in data mining terms. They're not saying this is a classification problem, or this is a regression problem, or this is a clustering problem. We're asking a question from the context of the business. Who should I target in this advertising campaign? And the reason we have this business question is so that we can narrow down the focus of the data mining project. If we don't narrow it down, then it's a fishing expedition. It's just so open that we won't be able to solve it. And you're going to find this in your assignment, because in your assignment you need to determine this business question in your first assignment. And if you don't do that very concisely, you'll find that it's very hard to do the assignment. So we've got our business question. Next thing we do is assess the situation. So where is the business now? Where are they in terms of the data mining of this business problem? Third question, let's work out the data mining goal. So now that we know what the business question is, can we transform that into a data mining question? So I'm going back to the example I gave before of where the business question was, which customers should I target for this advertising campaign? Well, we can transform that into a data mining question. So the data mining question might be, for all of the customers in this list, classify whether they will, yes, accept the advertising offer, or no, not accept the advertising offer. So now we have a data mining term in there, classify. So it's a classification problem, and now we have a data mining problem. Let's classify these customers. And the last part of business understanding is to produce a project plan. How are we going to get there? So this is really more for larger projects where it might be quite a complicated problem. For a smaller data mining project, this might not be as necessary. But definitely the business question and the data mining question are things that every data mining project is going to have to be looking at. The next phase is data understanding. Here we're going to collect the initial data. So we may be looking over the organisation and pulling data from different areas. Next stage is to describe the data. Can we understand what the data is about? And often what the output of this part is a data description report, where we look at all of the attributes of the data and we describe what each of those attributes means. So cust_ID might be a customer ID, and so on. The next part is exploring the data. So what's immediately obvious from the data? If we're really lucky, maybe we can immediately solve our data mining problem and our business question just from exploring the data. But generally we'll need to do a bit more. But this exploring the data is going to help us along that trip. And the fourth thing we might do here is verify the data quality. So what are the problems with the data? This is a really important step, because if we have dirty data, then we're not going to be able to solve the problem. It's going to be, you've heard the phrase garbage in, garbage out. Well, this is very true in data mining. And sometimes what people do at this stage is something called a data audit. So they go through and they work out where the missing values are, where the errors in the data are, and they can then think about how they're going to fix those problems up. The next phase is data preparation. Here we're going to select data. So we don't need all of the data, we want to collect some of the data. So some attributes might be important and some are not. So we need to think about exactly what data is important to solve the problem. Next stage is cleaning the data. Here we're going to deal with the data quality problems that we found in the earlier phase. And this is often 60% or more of the effort of a data mining project. Next thing to do is to construct the data. So we might need to create new instances or new attributes. There might be an integration problem or an integration issue, so we might need to integrate the data from different tables or records into one table or record. So I was doing a project some years ago for a newspaper, and we were looking at subscribers to the newspaper, and we wanted to predict which subscribers should be targeted in an advertising campaign. And we got the data from the paper was a national paper, so there were tables or data sets from every state, and they were all in completely different formats, and we needed to put all of that data into one format, into one file. So it's a data integration problem. Sometimes this can be quite tricky. And the final part of data preparation is formatting the data. So we might need to change the format of the data, for example, dates, and we might need to remove illegal characters and to fix up some of the issues. So some of the kinds of things that can happen are we might have, there used to be sometimes with data sets, if there was a missing value, instead of having a value in there, we would have the value 99999. So this is something that needs to be changed. Dates can come in different formats. Sometimes it could be American format where it's month, day, year, or Australian format where it's day, month, year, or it could be year, month, day. And all of these things need to be changed. Dates are a particularly tricky, error-prone kind of area in data mining because there's so many different formats. Addresses are another one. Okay, so at this stage we've got all our data prepared. Next stage is modelling. So we want to select which modelling technique we want to use, and there's different assumptions with each of the techniques, so we need to be cognizant of those and to make an informed decision. We may want to generate a test design. So how are we going to test the quality of each model and how valid it is? Next stage, we want to build the model, so we run some kind of modelling tool on the prepared data, and that creates a model. And the final thing we want to do is assess the quality of the model. So we're doing that based on some intrinsic measures about models. So for example, if it's a prediction model, if we're trying to classify some data, then there might be an accuracy of that classification. We might be able to say 70% of the data points will be correctly classified, but 30% won't. Generality is all about how well the model will work on data it's never seen before. If we're trying to do the unsupervised methods, if we're trying to just understand the structure of the data set, then there's different kinds of measures we use. For example, we might be doing measures on how well the model sorts our data points into similar kinds of clusters or groupings. And we probably need a domain expert to help us to understand whether the models are good or not. The next phase is evaluation. Here again we're evaluating the results of the models, but instead of evaluating them based on just their accuracy or some other measure like that, we're evaluating the models based on how well they solve the original business problem. So we're going back to the business question again. There might be a review process, so here we might be doing quality assurance and seeing whether the project missed any important factors or things in the business problem. And then we might be determining the next steps. So do we need to do something else to solve the business problem, or can we move directly to deployment? And then the final phase, if everything goes right, is the deployment. So depending on the size of the project, we may need to plan this deployment. For example, we might be need to develop some kind of strategy to get the insights back into the business. So deployment can take many different forms. It might be a case of giving a presentation like this, or there might be a report, maybe to the board members, the company board members, or there might be even more than that. We may need to develop some software so that the model goes right into the business. So another little story. I had a student a couple of years ago that was looking at a fraud detection problem. He was working for a company, and they were interested in understanding which of their accounts were fraudulent. And he built a model that did a really good job at solving this. It was something like 96% accurate on the test data that he was looking at. So he's quite pleased with that. But the final deployment was a piece of Java software that he wrote that the company ran each month that would highlight the accounts that it thought were fraudulent, and then people could look at that. Previous to that, they'd had someone just looking at all the accounts, and you can tell that would be a really long and tedious and boring kind of project, kind of thing to do, the kind of thing that a student would be employed to do. But his software would run, and it would make that list much shorter, and it would be much easier for people to review the accounts. So that's an example of a kind of deployment that is a bit different to just a report or a presentation. The next thing we might need to do is plan monitoring and maintenance. So we might need to maintain we'd almost certainly need to maintain the deployed model. So there's an assumption often with models that the underlying way that the problem that's being solved doesn't change. And often that kind of assumption is fine. So let's take, for example, the research work I'm looking at. So we're trying to predict the relapse of whether a cancer will relapse or not. The underlying way that the biology works in the body remains the same. The problem stays the same. If we can solve it now, then the same models to predict relapse will probably work in 10 or 15 years. But that's not the case with all kinds of problems. Fraud detection is a good example. So if we can predict fraud now, fraudsters are trying to produce fraud that gets past that. So the underlying problem, the underlying way that the fraud happens changes. So the model that we built before may not work in the future because the underlying thing that's happening, the way that fraud is being done, changes as time goes on. So what can happen is that models can go stale. People say they go stale, so they stop working. So we may need to maintain that deployed model in some cases. We would probably need to produce a final report describing what happened and maybe some kind of presentation to the customer. And often this is quite a difficult thing because you need to explain the data mining problem to a customer, and they don't understand about data mining. So you have to explain it in a very clear kind of manner. And finally, we probably want to review the project and reflect on how it went. So what worked really well, what didn't work very well, and we have hints for future projects. So that's just sort of an overview of the 6 different phases in CRISP. This slide is just talking about identifying the business problem. This is not always a very easy thing to do. So we could imagine that we have a major telecommunications company and they might identify their problem as churn. Churn is where customers move to another company. So they might have an account, a mobile phone account, and then after a certain amount of time they move to another company because they stop liking the first company. So the business problem might be, can we predict churn? Can we predict who will churn? And then maybe how to stop or decrease it. So they may have found that unemployed people over 80 years of age had a really regrettable tendency to churn. They didn't keep those customers. So their business problem might be, how can we stop or decrease this churn? Well, after they investigate a little bit further, they may find that the unemployed people over 80 actually died, they passed away, and that there was no incentive program that they could devise that would have any impact on decreasing that churn. It's simply not, obviously simply not possible. So maybe that's not the business problem they should be looking at. Maybe the business problem that they should be looking at is how to improve the return from underperforming market segments. How can they find different groupings within their customers that are underperforming and improve the return from those segments? So you can see it's a slightly different business problem. Obviously, you're not going to understand much about that business problem without talking to the domain experts. The next thing we're going to look at is how we go about surveying the data. So we would have some initial questions. What's in the data set? What's in the data set? Is what's in the data set able to answer the questions in our business problem? And where are the danger areas in the data set? Where does it seem to be really dirty, or where are there lots of missing values, or where are there problems in the data? So surveying the data helps us to understand those and to find the structure in the data set. So there's usually some insights in just the relations in the patterns and the patterns in them, but at this stage it's really early. We're really just exploring the data, so we're not trying to explain or evaluate those patterns. Let's look now at some fairly basic ideas in data, instances and attributes. So the first thing we're going to look at is objects. So we can think of an object as some collection of features, and we can take measurements of the features. So an example would be a car. So a car has some features. It has a fuel consumption, and we can measure that in miles per gallon or litres per 100 kilometres. Another feature it has is cylinders, or horsepower, or weight, measured in kilos, acceleration, or year. So that's like the general idea car. It's a little bit like a class in object-oriented programming. Then we can have instances of objects, and they're specific cars, and they're described by some set of values for the features. So we could have a specific car that has a specific fuel consumption, number of cylinders, horsepower, weight, etc., etc. So the object is a general thing. The instance is one specific object. So let's look now at a number of ways of describing our data. So here we've got a data set called University Friends, and you can see it just looks like a spreadsheet table. So each of the rows in our table each row is an example of a person, or from back on this page, an instance. So an instance of a person. So Carmen is an instance, Joan is an instance. So because data mining and data analytics has come from various different areas, there's often different words, synonyms for different words. So for example, instances is often called instances. It can also be called examples, or cases, or records, if we're thinking more from a database point of view. We have rows or measurements. And then the things that we know about each of these instances can either be called attributes, descriptors. Often we use the word features, fields, or columns or variables. Often we'll call them rows or columns, or instances and attributes, or features. But all of these words mean the same thing. So let's just look at a couple of examples. Here we've got the data set. We're only going to look at the part of the data set that's inside that red rectangle. So we don't want to know about the name or the lives near. So the data mining task might be, can we characterize the type of person that got sunburned last summer? And out of our table, we're only going to look at the hair, the height, the weight, the load, whether they had suntan lotion, and then whether they got sunburned or not when they went on the beach. So the last one, whether they got sunburned on the beach or not, that's often called the class or the target attribute. And usually this is the thing we're trying to either characterize or to predict. The data set in whole, So inside the red square is called the mining table. So one way of characterizing people that got sunburned is with a method called a decision tree. And the decision tree for this could look like this. There's lots of other ways to characterize it, but this is just one very popular example that we'll see a little bit later as well. And the way that you read this diagram, it's called a decision tree. It's sort of backwards to normal because the leaves of the tree are at the bottom, the bit that says sunburned or no, and that's our target or the class. And the ones in blue are other attributes. And these are the attributes that we're using to characterize or to make the decision. The way we read it is that we can say, first off, we can look at the hair color. So if the hair color is blonde, so we're following that first branch, if the hair color is blonde and they didn't have suntan lotion, then they got sunburned. If the hair color was ginger and they didn't have suntan lotion, then they got sunburned. Otherwise, they didn't get sunburned. So the way that we can characterize people who get sunburned is they either have blonde hair and didn't have lotion, or ginger hair and didn't have lotion. Otherwise, they didn't get sunburned. So that's just a way of characterizing this class. Let's look at another example, and you can think of this, first off, you can think of this as a predictive problem, because if we learn that characterization for this data set, then we can come along with another person. Say, for example, me, I have blonde hair, I'm short, average weight, and I didn't have suntan lotion, then did I get sunburned or not? We can tell that. The other thing we can tell is that because of our model here, we know that only hair color and suntan lotion are important for characterizing whether someone got sunburned or not. So we don't care about their height or their weight. They're not important to the problem. Okay, let's look at another problem. Here we're trying to understand who has better access to their friends. And we're going to look at just the name of the person, and the last column is who they live near. So for example, the first row, the first instance is saying Carmen lives near Ricard and Carla. And one way to answer this problem is to draw a dot on the page for each person and then draw an arrow between the two dots if they live near each other. And if you were to do that, you get this kind of diagram. And you can see that the data set breaks into three groupings. We've got two small groupings. Manu and Isabel live near each other. Joan and Francesca live near each other. And then there's one other big grouping where Carmen, Carla, Ricard and Jose live near each other. And we can even say that the people who have best access to other people, the most connected people, are Carla and Ricard because they're the most connected to it. They have the most connections to other people. This is an example of the other kind of data mining, making sense of the data. We're not trying to predict anything, we're just trying to make sense of it. On this slide, we're looking at relationships between instances and attributes. So each instance, of course, is described by a set of attributes, and we can take measurements for each attribute. But the attributes might be independent of one another. They might not have any relationship with each other, but that's not, and in fact, we often assume that about our data sets, but that's often not the case. Usually, attributes have some relationship to each other. So for example, if we had a data set that had dieters in it, so each instance is a dieter, and then for each person we have their name, their height, their weight, their body mass index, and their age, well, body mass index and weight and height are not independent of one another, because body mass index is calculated as the mass of a person in kilograms divided by their height squared. So people who have a high mass are going to have a high body mass index. So there's a relationship between them. And that's often really important to know because we might want to get rid of some of those attributes. Another common example is the price of something and the GST of something, because GST is based on their price. The next thing we'll talk about in a few moments. It's just talking about the different kinds of ways that we measure attributes. Let's look at a couple of tools now. The first one is R and Rattle. So data analytics tools in general, there's many of them. And they break into two kinds. There's closed source tools. So there's things like SAS Enterprise Miner, which we're probably going to use a little bit later in semester when we talk about decision trees. There's IBM SPSS Modeler, there's Microsoft SQL Server, Oracle, and MATLAB. So these are the proprietary pieces of software that are put out by these different companies, SAS, IBM, Microsoft, Oracle, and MathWorks. So there's open source alternatives to do all of these kinds of things. So there's a language called R that we will possibly use this semester, and built on top of R there's a package called Rattle. There's RapidMiner, there's Weka, there's Orange, and there's KNIME, and we'll be using KNIME as well. So probably this semester we'll use R and Rattle, we'll definitely be using KNIME. So let's look very briefly at R. So R is, well, for a start, R is really hard to look up with Google on the internet, because if you type R into Google, you get a lot of matches or a lot of hits as you can imagine. So R is a language. It's called R because it's a free version of a language called S, and S is for statistics. So R is this sophisticated statistical software package. It's quite state-of-the-art. When researchers do work, they often publish it as packages in R. So it's really up-to-the-date kind of stuff. It's quite powerful. It's cross-platform. It works on Mac, Windows, Linux. It's open source. It's free. This next thing is the link towards R, so you can download it. So it's a language and an environment for statistical computing and for graphics. If you're going to use R, I wouldn't necessarily use just standard R. I would suggest that you use something called RStudio. And RStudio, if you just type in RStudio, you'll find it. RStudio is just a really nice graphical user interface for programming in R. You can think of it as like a development environment, an IDE. So R is available for Linux, for Windows and Mac OS X. It contains many packages, many as in thousands and thousands, maybe 4,000. And they implement a whole lot of different statistical and data mining and data analytic kinds of things. All of the packages and the code for them live in something called CRAN, which is the Comprehensive R Archive Network, and there's mirrors around the world, so it's quite easy to and quite quick to get. And the idea is that you write R scripts in files and then you run them like programs. So that's a little bit complicated, so we're going to use something called Rattle. So this is a picture of what just bare bones the R console looks like. So you type things into this command line environment. This is just an example of 3 plots from R. One of the things that R does really well is to do nice graphs. So on the left-hand side, you can see a histogram. In the middle, that's another kind of histogram. And on the top right, that's box plots. And we'll see some of these things in future weeks where we look at data exploration. As I said, R is it can be a little bit tricky. There can be a learning curve which is a little bit difficult. So often what I think is nicer to use is something called Rattle. Rattle is a graphical user interface that can be used to do data analytics. And what it does is it puts up a window and you can just do a few options in it. And then in the background, it's calling R code. And what's really nice is you can look at a log to see what code it's calling, and it allows you to learn R really easily. The other thing that's quite nice about it is that it matches up with the CRISP-DM phases. So in the past, we've used Rattle. The picture on the right-hand side there is a book by Springer called Data Mining with Rattle and R, and that teaches you how to use Rattle. It's a very nice book. In fact, I used it as a textbook a couple of years ago. But I've sort of moved a little bit away from Rattle lately because it doesn't work all that well on Mac OS X. If you're using Windows or if you're using Linux, then definitely I would suggest have a look at Rattle. It's really nice. So Rattle is written by a guy called Graham Williams. This is a picture of Graham Williams. Graham's a director of data mining at the Australian Tax Office. And Rattle has been used at the Australian Tax Office, so it works really well in a complex industrial setting with large data sets. As I said before, Rattle matches up really nicely with the CRISP-DM phases, and there's a tab for each of these phases. So the first one is to load a data set, so the first tab is called Data. Second one is to select the instances and attributes for exploring the data. There's an Exploration tab, a Transformation tab, and then there's a tab for doing the modelling, a tab for evaluating the models on different data sets, and then there's even a tab for exporting the models for deployment. Just to give you just a few pictures that sort of show each of these different phases. This is the first one where we're loading the data. And you can see you can load the data from a spreadsheet or from other kinds of things. That ARFF is a special format that's used for Weka. ODBC is a database connector. The next couple are our dataset, our data file, and library from R. And we can even run a script to get the data. There's ways of partitioning the data, and the big part at the bottom there are the different attribute or variable names, and then we can say whether they're input variables or the target that we're trying to predict, or other kinds of things. This is the Explore tab, and this allows us to look at each of the different attributes and then to produce little maps and plots about them, or to do other kinds of things like correlation diagrams and whole kinds of things. This is an example of the test. So we can do a whole lot of statistical tests, correlation tests, and so for example the Kolmogorov-Smirnov test allows us to tell whether two attributes have the same distribution or not. We won't be using that too much. This is the tab that allows us to transform the data, so we can rescale it, or we can recode it, or we can normalize it in different kinds of ways. So we'll talk about data preparation in a week or two, and these kinds of things will make a lot more sense then. The next tab is all about modeling the data, and here we're using something called a decision tree to build to classify the data. The problem we're looking at here is trying to classify whether it's the weather in Canberra. So we're trying to predict whether it will rain or not in Canberra. And the part at the bottom is a description of what's happening with that classification model. You can see at the top where it says type, there's a whole lot of different kinds of modeling techniques that we can use. So we can use tree, we can use a random forest, we can use boosting. SVM stands for support vector machine, so we'll be talking about that later in the semester. Linear is linear models. Neural net is an approach called an artificial neural network. And there's different kinds of, and there's a whole lot of parameters that we can set with them. This next diagram just shows a decision tree like we saw before about whether it's going to rain or not in Canberra. So it's saying if the pressure at 3 p.m. is greater than or equal to 1011.9 millibars, and the cloud at 3 p.m. is less than 7.5, then no, it won't rain. If the cloud is greater than 7 or equal to 7.5, then yes, it will. So we can build a decision tree like this for our models. The number underneath is the accuracy of the results for each of those. And the final tab is called the log, and this is the actual R code that's used so as you fill in the parts of the in the other tabs and you do different things, it generates code and puts it into this log. So you can actually copy this code out and put it into the command line interface, and you get the same results as just running Rattle. So it's a really good way to learn and to understand what Rattle's doing, and also to make it do some of the things it can't really do. The other tool that one of the other tools that we'll be looking at this semester is called KNIME, and KNIME is another open source piece of software. that's developed from Germany, I think. Yeah, Konstanz, Germany. So it's quite easy to deploy. It's easy to use, and it doesn't do all the things that R can do, but it does some things much more easily. You can download it from www.knime.org. You should be downloading something called the KNIME application. So it's compatible with R, MATLAB, and Java. It's also compatible with Python, I think. You can call any of these things through nodes in KNIME. You don't need to download any packages in KNIME like you needed to do in R, but you do need to remember to download all the add-ons. When you go to the download page, there's a couple of different examples. You can either download bare bones KNIME, or you can download all free add-ons, I think it says. You should download those, otherwise there's going to be a whole lot of things you won't be able to do in KNIME. And just like R and Rattle, KNIME's available in Linux, Windows, and in Mac OS X. This is a picture of what KNIME looks like. So you can see on the left-hand side there's an explorer and then a set of nodes. And each of these nodes is associated with something that you can do in KNIME. The big section in the middle is called the workbench, I think, and that's where you make like a diagram that shows what you're doing. On the right hand side it says node description, and that's almost like the help for KNIME that tells you how to use it. At the bottom, outline is just a zoomed out picture of what's in that top diagram, and then KNIME console is a log of any warnings or errors that you're seeing. So normally you'll see something like this. You can see in the bottom on the middle, you can see how the big picture of the workbench is, and you can see a zoomed in version there. And each of those little coloured squares is one of the nodes that comes from the node repository, and it shows how the workflow fits. So looking at each of these areas, the part in the red there is a list of existing workflows. On the bottom left, all of the packages and the algorithms that you want to use fit inside this node repository. And you'll see there's like little tiny triangles there. They're like folders, so you can open up I/O, for example, the first one, and a whole lot of other packages and other algorithms will be inside there. So there's quite a lot of different nodes that you can use. This bit at the top is used for running the models and for debugging them, and for other kinds of things that you might want to do. So what you do is you'll be looking at the things in the node repository, and you drag the nodes and put them into the workbench. So for example, here we're dragging a CSV reader node into the workbench. CSV reader is a node that allows you to open up a CSV file on the computer and then read it. CSV stands for comma separated variables. It's just a really standard format for storing data. You can have, in Excel, you can export your data in CSV format. It's just a really simple text file. So you can see underneath the node, there's like a little rectangle with a red dot, and then there's two other grey dots. Those dots tell you how far you are through, how prepared that node is. So if it's red like it is there, it says that your node isn't ready. And what you need to do is you need to set a whole lot of parameter settings. So if you were to go to that CSV reader and right click on it, you can set the configuration options. And in this case, it's things like pointing the CSV reader to a real file on the computer. So after you've got those set correctly, it changes from red to yellow. So in this case, it means that the data is here. And then the final thing that you can do is to execute that node, and that means it'll go and actually read the data from that file and store it inside KNIME. And then the little light goes to green. So it's like traffic lights going from red to yellow to green is ready to go. So here it's executed OK and we're ready to go. Now, when you get your nodes, you link them together with a little arrow. And the little arrow is like a pipeline that shows where the data's going. So it's coming from the green one, so from the CSV reader to here it's a column filter. So this is saying that when we read the data from the CSV file, all of that data will be sent to the node column filter. Column filter allows us to look at just one attribute or one column or several columns of the data set. So this is just a way of filtering out some of the data. So the lines just mean that's how the data flows. And you can see it's really easy to remember which one's the output and which one's the input, because it comes out of the little triangle and into the other triangle like an arrow. So when we run our nodes, we can see something called a results window. So if you right click onto the CSV reader, there's usually an attribute or a menu item you can select that shows the results. So here in our CSV reader, we can open up the CSV file and we can see what's on the table, and that's what's being shown inside that CSV reader file table window. And what it's showing is we've opened up something called the iris data set. So iris is a very common data set in data mining. We'll see it many times this semester, which is just measurements for describing particular species of an iris flower. And you can see for our first row, number 2, we have 5 different attributes. The first one is has the value 4.9. The D means it's a double. Then the second attribute has the value 3. The third one has the value 1.4. The fourth one has the value 0.2. And the last one is a string, that's what the S means, that has the value setosa, which is the type of iris. And you can see, this is not to do with the results window, but it just happens to be on the screen as well. You can see in the node description, that's like the help that describes that CSV reader node. So when you click on a node, it puts a little square around it, and it fills in the value for in this case CSV reader, which tells you what the node does, and then tells you what the dialog options are when you're setting up the node. Okay, so that's probably about it for KNIME for the moment, but we're going to go through this in a lot more detail over coming weeks. So let's now look at different kinds of attributes types. So with attributes, there's essentially 4 different types. The first, so these are nominal, or often called categorical. So nominal, ordinal, interval, or ratio. And these describe the different things that an attribute can do. So it's a level of properties. And sometimes it's not often clear how to fit an attribute into being whether it's ordinal, interval, or ratio. It really depends on the meaning of or the semantics behind the attribute. So let's look at each of these different attributes one by one. So the first one is nominal or categorical attributes. So here the values are distinct symbols. So the values are labels, and nominal just comes from the Latin word for name. So as an example, we might have the attribute hair, and it has the value blonde, brunette, or red. So there's no relationship between these. Like we can't say blonde is better or bigger or whatever than brunette. It's just different to brunette. Same with postcodes. Even though they're numbers, they're really labels. We can't say that the postcode having a larger value than another means anything. Industry codes or field of research codes are similar. So there's no relationship between these nominal attributes. We can't order them in any way, and we can't get a distance between them. We can't get a distance between red hair and blonde. So because of that, we can only do equality measures. So we can say something like, if hair is blonde or lotion is no, then on the beach is sunburned. So hair is blonde. We can only say whether it's equal or if it isn't equal. So that's the first one, nominal attributes. The next one is ordinal attributes, and here we have an order to the attributes, to the values. So the There's transitivity, so we can say that it's less than or greater than, but we can't get a distance between them. So as a couple of examples, let's have height. So we can have height with values tall, average, or short. So we can say that tall is larger than average, and average is larger than short. But because we're using just tall, average, and short, we can't subtract them. It doesn't make sense to say tall minus average equals something, or tall or average plus short equals something. There's a special case with binary attributes. Sometimes we can take them, even though I guess they're ordinal, we can still take the mean of them or make probability distributions. So that's our ordinal, we can just order them. Next one is interval. So interval attributes, not only are they ordered, not only can we check whether they're equal or not equal, but they're also measured in fixed units and fixed and equal units. So here we can say something like height as measured in centimetres, or weight as measured in kilograms. And here we can say the difference between the two values makes sense. So there's a distance between things. But we can't use sum, we can't use product or ratio, it doesn't really make sense. And usually the problem with this is because the origin isn't the same. So as an example, we can talk about 80 degrees Fahrenheit is the same as 25 degrees Celsius, or 40 degrees Fahrenheit is the same as 5 degrees Celsius. So we can take a difference. We can say the difference in degrees, but we can't really say whether it's twice as hot or 5 times as hot. The last type of attribute is the ratio type. Here we can do all of the things. We can say whether they're equal or not equal. We can order them. We can add and subtract them. But we can also take multiplication and division. So we can have age in years, or we can have income in thousands of dollars, for example. So we can use all of the mathematical operations. One thing that's a bit weird is ratio type. We can have, sometimes it can be dimensionless, so there can be no way of measuring it. So for example, we could talk about traffic lights. So traffic lights could be green for some number of seconds and red for another couple of seconds. So we could have some kind of new attribute called the throughput coefficient that would be divided by the number of seconds in green divided by the number of seconds in red, but there's no measurement unit anymore for those. So that can sometimes be an issue. The other thing that we're interested in with attributes is we can have scalar versus non-scalar attributes. So scalar attributes are just a number. So there's just two components to them. The first is the value of the attribute, so that's a number. And the second thing is the scale that it's measured in. So for example, we can talk about the speed of a car, and that's just measured in a single number of kilometres an hour. So we can say the car is going 60 kilometres an hour. So there's really only just one thing there, but two components. So value, 60, and the scale, kilometres per hour. So we can contrast that scalar with vector. So vector, we have a number of components. So there's a whole lot of different values with their measurements. So for example, we can say the velocity of a car is described by some number and a direction. So there's the direction it's going plus the number. And often with in data preparation, vector values are just treated as a whole lot of different scalars, and then we look at the rules for each scalar separately. Just to give another example, here we have the speed of a car is 120 kilometers an hour, so car is 120, whereas the velocity of a car is 120 kilometers an hour northeast, and there's 120 and 45 degrees. So just to summarize, the first is our nominal attributes, and the only thing we have here is the property of distinctness. So we can only say whether nominal attributes are equal to or not equal to. At ordinal, we can do everything that nominal can do, plus less than and greater than. At interval, we can do everything that nominal can do, ordinal, plus we can also do plus and minus. And then ratio, we can do all of the not equal, unequal, less than, greater than, plus and minus, but we can also do times and divide. This next slide is just some examples of each of them. And here, I'm not going to go through them in example in detail, but it's just for you to see for nominal what the description of it is, what some examples of each different type of attribute, and then some of the operations that we can do on them as well. We're not necessarily going to go through all of these operations in detail, but you can look them up if you like. The other thing we're interested in attributes is whether, or specifically numbers, is whether they're discrete or continuous. So with the discrete attribute, there's only a finite or countably infinite set of values. So, for example, postcodes or sets of words in a collection. So generally these are things that can be represented as integers on a computer. And binary is a special case. And we can contrast that with continuous attributes. Here, instead of storing them as integers, we store them as real values or doubles. So things like temperature or height or weight. That said, because of the way that computers work, we can only store real values using a finite number of digits, so they're typically represented as floating point variables. So we can't store every single continuous real number, but we can sort of treat them as such. So let's now look just at some data sets. So this is a picture of showing different kinds of data sets around a medical theme. So we can have record data sets, and we're going to go through each of these in detail. So record data sets are essentially things that you can see in a spreadsheet. We have graph data sets, we have ordered data sets, and then we have structured or semi-structured or unstructured data. So we're going to go through these in detail, but first I want to talk about a couple of important characteristics of the structured data. So I should say structured data is the first three: records, graphs, and ordered. So the important characteristics that we're interested in are dimensionality, sparsity, and resolution. The first one is dimensionality. So here we're interested in the number of attributes associated with each record. And it turns out that high dimensional data is quite challenging and difficult to work with, and there's a thing associated with high dimensional data called the curse of dimensionality. We'll talk about that in a minute. Sparsity is all about how many zeros you have. So we might have a record that has many, many, many zeros, but only a few attributes that aren't zeros. And again, that brings up a whole set of issues. The third characteristic is resolution, and here the type of patterns that we see depend on the scale that we're looking at. Often this is the case with time series data. So for example, with sales figures, say for example sales of chocolate, depending on the scale that you're looking at, daily, weekly, monthly or yearly, you see different kinds of trends. So for example, trends with sales of chocolate are going to peak during Easter around April or March, and around Christmas time, and probably around February for St. Valentine's Day. So you may see quite different patterns weekly compared to yearly. Now, by the way, this is quite a long lecture, so if you want to break, this is probably a good time to break. So, assuming you've had a break, let's now look at the curse of dimensionality. So, this is an interesting term. So, it was the curse of dimensionality is a phrase that was coined by a guy called Bellman, and it's all about the idea that the more dimensions of data that you have, in some ways the harder the data is to work with. This seems really counterintuitive, because you'd think that the more dimensions of data you have, the more things that you know about each attribute, that should help you with doing predictions or understanding the data. But it turns out that that's not the case. In fact, as the number of dimensions increases, you need much more. So if as the number of attributes increases, you need many, many more instances of data or data points to understand what's happening, the underlying space underneath the data, so to understand the structure of the data and to make very good predictions from it. And one of the best descriptions of this that I've found is from a book by Christopher Bishop called Pattern Recognition and Machine Learning. It's a really nice book that talks about a lot of these data mining kinds of problems. I highly recommend it, although the maths is a little bit difficult in it. So what we're going to do is plot a data set in 2 dimensions, and we're going to use the neighbours of a data point to classify that data point. This is using something called K-nearest neighbour classification. We're not going to really talk about it in class, but it's a really simple, straightforward approach to doing classification. So here's our data set. So it looks a bit weird. We've got 2 attributes. One is called x6 and the other one is called x7. So they're pretty crappy names for our attributes, but they're the ones we've got. The actual data, I think, is it's flow of oil through a pipe or something, but honestly it doesn't matter. So you can see we've plotted every single data point according to its value of x6 and x7. And we have 3 kinds of data points. We have red ones, and we have green ones, and we have blue ones. And these are 3 classes or types of data. And the problem that we're trying to do is, for a particular data point, we want to try and where we know the x6 and the x7 value, we want to predict whether it's red, blue, or green, the class. And you can see about a third of the way across and a third of the way down, there's an X, a little cross. So we want to say, for that X, what colour should it be? Should it be a red X, a green X, or a blue X? So a really simple way to do this is to break up our grid. So we've got, you can see we have 0 to 0.25, 0.25 to 0.5 along the x6, and then 0.5, 0 to 0.5, 0.5 to 1, etc. for x7. So we're going to break up this square into a whole lot of little squares, and then that little square, we're going to make it the colour that has most of the points in it. So let me show you on the next diagram. So here we've divided up, and you can see, say in that top left-hand square, most of the data points inside that square are blue. So we're going to say that's a blue square. So there's 2 reds and 1 or 2 greens, 1 green maybe, but because most of the data points are blue, it's a blue. And you can see that the squares are the different colours. The one below that, for example, there's slightly more red dots than green dots, so we're deciding it's red. And what we're going to do, if the data point we're trying to classify is in that square, then we're going to colour it the colour that square is. So for our X, because most of the data points in that square are red, we're going to say it's red. So you can see it's a really straightforward approach. It's actually, I wouldn't recommend this in practice because you can see it's not necessarily very good. There's issues where you cross from one square to the next. So for example, in the second row on the very right, you'll see 1 green square, but that's only because it's got 2 greens and 1 red. But you see there's a couple of reds that are almost on the edge. So if you had had 1 of those or 2 of those in that square, it would have flipped from being red to green. And the same in the border between the blues and the reds. You can be just a little bit on one side and you'll flip them from being, for example, in the 3 across and the second one down, the reds are much further down, but if you were, so probably it could be red, but even if you were a little bit further past that, you'd suddenly be red rather than blue. So it's not the best approach. generally this approach of dividing up the block into different squares and then classifying based on how based on the neighbours works really well, but it has serious problems when you run into when you have high dimensional data or even a few dimensional data, and that's because the number of regions that you need to understand grows exponentially with the number of attributes. So in the diagrams underneath, let's look at the first one on the left. So here we have one-dimensional data. So you can see we've divided up the data set into three areas. So there's the first one, second one, the third one, and then there's, forget about the values after that. So to be able to classify a point along that line, we need to understand data points in three regions. So when we move to two-dimensional data, you'll see that to be able to classify a point within that space, we need to now look at 1, 2, 3, 4, 5, 6, 7, 8, 9 spaces. So we need to understand what's happening in each of those 9 spaces to be able to classify a point. And the problem gets even worse when we move to 3 dimensions. So you can see in 3 dimensions we have 27 cubes. So we need to understand what's happening in 27 cubes to be able to classify the point. So you can see this makes things different. So with one-dimensional data, we need to understand 3 spaces. With two-dimensional data, we needed to understand 3 squared spaces. And with three-dimensional data, we need to understand 3 cubed spaces. So you can see that the number of spaces increases exponentially with the dimensionality. So, and if we don't understand the underlying space very well, then we can't make good predictions or understand the structure of the data. There's other problems that go hand in hand with this, and I'm not going to go through these in any kind of detail, but just to give you sort of an idea, often when we want to model regions, we often do it with polynomial expressions. And what happens is, as you increase the dimensionality of the data, then the number of parameters to describe that polynomial, cubic or quadric or whatever, increases too quickly. Also, and this is quite weird, distances don't work very well in high dimensional space. Let me say that again. Distances don't work in intuitive ways in high dimensional space. As humans, we live in three-dimensional space, and the way that we understand distances between things in three-dimensional space isn't the same as distances in very high-dimensional space. So it turns out that in high-dimensional space, most of the volume of a sphere ends up concentrated in a thin shell near the surface of that sphere. So it turns out that most of the points that are in high dimensional space tend to be near the edges of regions in that space, which means that we need to extrapolate between the different regions. That's like looking at this at the spaces between, say, the blue and the red squares or the green and the red squares, rather than within the squares. And that's more difficult. This picture on the right-hand side is trying to show the epsilon on the x-axis is the thinness of the sphere, and the y-axis is the volume of the sphere that's within that shell. So you can see that as the dimensionality increases, the volume of the sphere is mostly concentrated in a thin region on the outside of the sphere. If that doesn't make sense, don't worry too much about it. We'll talk about it more in the future. So even though the cursive dimensionality is important and we need to be aware of it, it turns out that it doesn't really stop us doing data analytics. And the reason for that is because of two things. First off, even though real life data might be very highly dimensional, it actually lives in something called a lower dimensional manifold. So even though it seems to be highly dimensional, most of those dimensions maybe don't matter. It lives in a lower dimensional section or part of that space. And the other thing is that there's usually local smoothness. So if we have small values in input values, you get small values in target values that we're trying to predict. So we can do local interpolation. If we go back to this picture here, you can see, say for example, in the blue squares at the top, if we move a little bit in one direction, it still remained blue. It doesn't suddenly go from blue to green. And even in some of the more mixed up areas, like the third one down and the third one across, you can see that if we move among those red data points, we stay red. We don't flip to green suddenly. So there's local smoothness. Okay, let's look at a couple of different kinds of data sets now, of structured data. The first is record data. So this is the kind of data we're mostly going to see. So record data is data that just is a collection of records. Think of it as the kind of data that you see in spreadsheet. So you have rows where that represent instances, and then columns that represent the attributes of each instance. So most of the data that we see is like that, or we're going to transform it so it's like that. We can have matrix data, so that's essentially the same as record data, except that we only have numbers in there. And that's quite useful because then we can deal with it using matrix mathematics. And we can think of the data in there as being points in some multidimensional space. So here we've got each of the rows is some point in 5-dimensional space. We can have document data. So this is text data, and each document becomes some vector in some highly dimensional term space. So the picture underneath is showing 3 documents, and each document has some number which you can think of as like the frequency or the number of times a word appears in that document. And each of the attributes is a potential word that can appear in that document. So cat, dog, pet, mat, sat. So we can say document 1, the word cat appears 3 times, but it doesn't appear at all in document 2. So we can transform a text document into this kind of format, and then we can understand that or make classifications. Transaction data is a special kind of record data, and here we've got each transaction has a set of items, or it's an item set. So here's an example of 5 transactions. So the first transaction, the person bought bread and jelly and peanut butter. And the second transaction, the person bought bread and peanut butter. So we can transform that into this kind of record data as well if we have an attribute for each of the type of item that we can sell, and a 1 or a 0 or a true or a false for whether the person bought that item or not. We can look at graph data. Graph data is looking at relationships between things, so we often see that with XML documents or HTML documents, or the way that people work. So we saw an example earlier with people and their friends. We can have ordered data, so here we have sequences of transactions. So this is trying to show that item A and B happened together, then item D happened, then items C and E happened together. So the things in the brackets are one element of the sequence, and each letter is one item or event. We can see ordered data often in biology. So this is an example of biological sequence data. So on the left is genetic sequence data. So we have G's, A, T's, and C's, and they're the nucleic acids that are associated with a gene. And here the problem is trying to see patterns within those sequences. So trying to find where maybe a gene starts or a gene ends or other kinds of things. On the right hand side is a protein sequence, and these are the amino acids that are making up a protein. So a protein is a sequence of amino acids. And here, again, we're also looking for patterns that match along that sequence. So we might be looking, they're often called motifs. So we might be trying to look for particular domains within a protein, or we might be trying to understand whether a protein is maybe a transmembrane protein, so it crosses a cell membrane or not. So there's a whole lot of issues with this kind of sequence data. The other type of ordered data we have is spatial data. So here we have data that is either ordered according to a space, or it might be ordered according to time. So it might be ocean temperatures, and they could be ordered over a time series, over months of a year or something. So with our data, we're usually interested in the quality of the data. So we want to understand what kinds of data quality problems there are. We want to understand how we can detect them. That's really important with very big data sets, because we can't look at every single record individually. We're interested in what we can do about these data quality problems, and again, especially automatically, because we can't usually go from data point to data point and fix them all individually. We want to do it automatically, but without causing more errors. So as some examples of data quality issues, and we'll see these in a few minutes, we can have missing values, we can have noise or outliers in the data, or we can have duplicate data. So let's look at each of these three in turn. The first one is missing values. So there's several reasons for missing values. Possibly the information wasn't collected. So for example, age or weight. So we may have data from people doing dieting, and there may be often women don't want to give their age sometimes, and maybe people don't want to give their weight because they might be embarrassed about it. So sometimes they'll just give a 0, or they just won't give a value for that. Or perhaps the attributes might not be applicable in all of the cases in the data set. For example, our data set might have annual income, and annual income probably doesn't make sense for children. So there's a whole lot of ways we can handle missing values. Some of the ways we might just get rid of the data objects or the attributes that have missing values. Often we can't do that because we might not have any data left if we did it. We might try to estimate them. We might just ignore them with the analysis, but we can't always do that. Or we might want to replace the missing values with all the possible values. And again, that doesn't always work. And we'll see some of these examples in a moment. So with our missing values, there's a difference between missing values and empty values. So missing values are values that haven't been entered into the data set, but there's an actual value that is in the world. It just wasn't put into the database. And we can contrast that with the empty value. Empty values are ones where there's no real world value that can be used. And it's usually really important to be able to differentiate between missing values and empty values in data analytics. Let's look at an example. So our example is a sandwich that's a shop that sells sandwiches. And they sell ham sandwiches. So we're not catering to vegetarians, but it's a ham sandwich store. And we're going to sell sandwiches that either have Swiss cheese or tasty cheese. And our shopkeeper is really interested in data analytics, and he wants to be able to predict his customer preferences and to control the inventory of cheese and bread, I guess, and ham. So he's going to keep records of what people buy. So the data that we're collecting includes two attributes. First off, he's going to collect the gender, so whether it's a man or a male or a female that buys the sandwich. And he's going to collect the cheese type, whether they bought a ham sandwich with Swiss cheese or a ham sandwich with tasty cheese. So let's suppose that someone comes into the store and they request a ham sandwich, but they don't want any cheese. So the salesperson is obviously totally bamboozled by this. So when they enter the data, the salesperson forgets to enter the gender of the customer. And then for the transaction, they obviously don't have a cheese type either. So there's a difference between a missing value and an empty value. Missing value is the gender because the customer is either male or female, so it's missing. But the cheese type is empty because the person didn't have any cheese. There was no cheese associated with the sandwich. So the gender is missing. There really was a gender, but it wasn't input. The cheese type is empty because there never was a cheese type for that transaction. So what do we do with missing values? In practice, we can detect them using out-of-range errors or by looking at empty spreadsheet cells. Often what happens is there may be some specific values. So in older databases, often if there was a missing value, it would be set to 99999. So why are there missing values? Well, there could be malfunctioning equipment. Someone might have made a mistake when they entered the data. There were changes in software. We might be merging from different data sources and we get missing values that way. It's also the case that missing values might have some significance in themselves. So for example, there might be a missing test in a medical examination. But we really need to look at the missing values and at least understand why they're there. It's also sometimes useful to look at the correlations between missing values in different attributes because you can often find out more information about that. So for example, in a dieta data set, you might find that height and weight are both missing values and there's a correlation between those. The second type of data error or issue is noise, and this means that the original values have some kind of modification. So an example is if you're calling someone on a mobile phone and there's quite poor range, sometimes your voice gets quite distorted. Or in the old days, for old televisions, you would have ghosting and some kind of image issues. Another issue are outliers. So with outliers, they're single occurrences or very low frequency occurrences of a specific value of an attribute that's very far from the bulk of the attribute values. So they turn out to be data objects that seem to be quite different to others in the data set. So we could think, is this a mistake? Sometimes it's a mistake, sometimes it may not be a mistake. So in the picture below, you can see that most of the measurements are in a few groups or clusters. Then there's some smaller clumps, and then there on its own is an outlier data point. So it could be a mistake in the data, and a value could have been entered incorrectly, but it might just be a really interesting data point. So they're usually something that we're interested in data mining. Occasionally sometimes we'll get rid of them because they can muck up the way that our models work. So for example, there's a method called K-means clustering. And K-means clustering tries to find groupings of data points. It's a way of making sense of the data. But outliers sort of throw it into a bit of a tailspin. And we'll see that in I think one of the later weeks this semester. Another thing that we look at is duplicate data. So the data set might end up having data objects that are duplicates or almost duplicates of others. This is often a big issue when we're merging data from different data sources. And often one common task in data analytics is washing data sets. So when you merge two data sets, you look to see if there's duplicates and then you get rid of them. And the reason you get rid of them is because they can cause issues. If you're trying to make a mailing list for people maybe they're interested in taking up an offer and you send phone numbers to a call center, well, you don't want to call the same person twice. It's a waste of time and it makes the person angry. There's sort of some subtleties in detecting duplicate data. So for example, the same person might have different email addresses, or they may be someone who changed their name when they got married. So there's a lot of sort of interesting kind of data linking and data duplication issues that need to be looked at in data mining. Okay, let's look now at data understanding. So data understanding, we often start with something called a data audit or a data quality audit. And we're looking at each of the attributes in our raw data, what type of data it is, so whether it's a nominal attribute, an ordinal attribute, and the others. We look at the possible values, and potentially we want to look at the semantics, the meaning of that attribute. And we're going to check for missing and empty values and perhaps see what we could do with those values. So you can see here there's an example set of attributes, and you can see we have a name of an attribute, we have their types, so nominal or categorical, we have some measured values. Sometimes you're obviously not going to put all of the values, and then there may be comments. Often you'll say this is the primary key, or other kinds of issues. In your second assignment, you'll be doing this kind of data audit for a data set. So the next thing we're interested in is data exploration and understanding. So we want to examine the values of the attributes. We want to look at the distribution of values for a variable, or the distribution of values for an attribute. That's important because we might see some interesting things. Is it normally distributed? Is it exponentially distributed? Is it bimodal? Are there a couple of distributions together? And that gives us understanding of that attribute. We can see whether the recorded values in the attribute are all valid. For example, do we have negative values for an age of a person? Does that make sense? Can we have 0? Does that make sense? We might look at the number of different values in an attribute. We might look at the frequency of each value. We look for empty or missing values. If the values are the same, all the same, then we probably want to remove it because it's not adding anything. So this would be an example where for one attribute, every single data point has the same value. We might be interested in sparsity, so where most of the values are 0, but occasionally a value is recorded, and we can often combine attributes together so that the attribute carries more information about a whole lot of attributes. And we'll see that a bit later. Next we'll do data exploration understanding. So the motivation for doing this is because we want to select the right tool for doing the analysis afterwards. And data exploration and understanding makes sense of something that people are really good at, and we can see patterns quite easily in data, at least in 2 dimensions or 3 dimensions. So the idea of data exploration is to make use of that and to let people immediately see patterns. So it's related to an area called exploratory data analysis. This is created by a guy called John Tukey, who's a statistician, and he wrote this book's Exploratory Data Analysis. You can download the book from this web link, and it's also linked on UTS Online. So data exploration is a bit open-ended. It's a little bit like a treasure hunt, and we're just looking for things. But if you approach it systematically, if you do the data audit, you look at each of the attributes individually, then in pairs, and so look at it systematically, then you can do it quite well. One of the good ways to go about it is with visual exploration, and we're going to look at that in a few weeks. So that's the lecture for this week. It was a bit of a long one. We should get some shorter ones later in the semester. So if you have any questions, please ask me or Dominic in class. Okay, I'll see you later. Bye-bye.